So, Vanakkam. So, we will continue our lecture on engineering seismology. So, we have been discussing about the estimation of the seismic hazard. Okay. So, we started with the how to prepare a seismotectonic map. So, we discussed with about the seismic steady area. So, where you need to estimate a seismic hazard. Then we also discussed a seismic steady area. So, SSA. Okay. So, where you have to consider all the source and seismic data to estimate hazard at steady area. Okay, that is a SE. Like I told you that Bangalore is a steady area. Your seismotectonic steady area, okay, the seismic steady area can cover a Mysore, Chennai, nearby large areas. It depends upon the past earthquake. We also discussed how to select a seismic steady area. So, what is the logic behind that? So, what are the parameters you should consider? So, we discussed, and then followed by we also discussed about the seismicity data. Okay, how to collect earthquake data, how to homogenize. So, what are the conversion equations are available. Okay, so then how to estimate a maximum magnitude. Okay, so what are the parameters you should consider, what are the methods are available. We also discussed what is the method I have developed. Okay, so then followed by, so the Mmax is the first and prime importance in the seismic hazard analysis. First, if we established a maximum magnitude, okay, at any region, okay, the next step is to estimate a distance. Okay, that is the second important parameter in the hazard analysis. So, the distance means where likely to earthquake going to occur, and from that point to the your steady area. Okay, so that distance varies from generally 0 from the your starting part of the steady area, if there is any source in that steady area itself, and then it goes to the maximum up to the end of the seismic steady area. Okay, so sometime it may be 450, 500, 300, it depends upon the seismic steady area what you consider. So, today class we are going to discuss about the source to site distance and then the recurrence relation. Okay, so this is the third important parameters in the seismic hazard analysis. So, the distance should be, as we discussed earlier, that so it is the point between the basically your epicenter. Okay, so the epicenter to the site. So, the site is basically your steady area. So, this point will be anywhere in your seismic steady area, SSS. Okay, the origin where it is called as a focus, we discussed that focus point. So, the projection is the epicenter. Okay, the distance can be, okay, so there are several way people will take. So, for example, epicenter to your point of interest is the epicentral distance. The focus to point of interest is called as hypocentral distance. As I told you that the beginning part, the Joyner and Bohr, okay, they told that the shortest distance from the rupture to the site. So, for example, this is the focus, but they end up in the rupture area like this. This is the rupture area. So, then this point will called as the distance closest to the rupture surface. So, similarly, the distance of surface projection of the closest point to the rupture. So, these are all the 4 widely used distance is adopted in the most of the predictive equations. Okay. So, but the modern equation whatever today they call, most of them they adopt a hypocentral distance. So, we should be clear on where to estimate this distance. So, this is a typical example shown with the fast earthquake. For the future earthquake, basically you should characterize the seismic source and then take where it can rupture, how long it can rupture, then you can estimate basically the distance of closest to the rupture surface or hypocentral distance. Okay, so, this distance should be feeded in the predictive equation. So, there are typical example how this distance can be taken. For example, if you have the vertical fault, okay, if you have the vertical fault, so how the distance you can see that the hypocentral distance, seismic response, the rupture distance and RJP, Joyner and Bohr, where the rupture surface projected is. So, you can see that, so among this basically whichever shortest can be considered for the highest worst scenario kind of things. So, this is the point source, again there is a like far away points, the R minimum, okay, so there is so much, so the R maximum so much, so the R minimum should be always considered. So, when the Mmax comes, you will be considering the maximum magnitude, when the distance comes you will be considering the minimum distance. Why? Because the R minimum will give the more hazard when compared to the R max. So, when you have the probabilistic approach, basically you consider a minimum to maximum with the variation in the distance. Okay, that is what we do. So this is a typically the dipping fault. Okay, so you can see the dipping fault. So R seismic, R rupture, R hypocenter. So then this is another dipping, so where you can see the RJP typo. So this is again the source of linear source. Okay, so where the R minimum, R max, the minimum should be taken if it the DSHA. So the PSHA, you will be making a small grid and take each grid a distance minimum. So the volumetric source you can see here. So like that, a different shape and size of the source will influence on your distance. So you should appropriately estimate a different possible distance and take a R minimum, okay, which will be the hypocentral distance. R hypocentral distance minimum should be taken as a measurement for estimating the any hazard values. So once you estimate the hazard values, the next part is actually the estimating the recurrence relation. So the recurrence relation basically gives you the repeatability of the earthquake in the region. So as we have seen that from the San Francisco the observed continuous data, so they highlighted that so it is not possible to predict a earthquake the recurrence very precisely, but how still for the calculation purpose we have to follow some kind of pattern. Okay, so that reason the Gutenberg-Richter recurrence relation is widely used in the engineering seismology and for the hazard estimation. So the Gutenberg-Richter recurrence relation, so what he related actually, so he related the number of earthquake and then a particular magnitude, you follow a trend. Okay, so that trend basically gives you the how the recurrence rate in the region. So the relation assumes that the potential distribution of the magnitude on every source, it also useful to estimate minimum and maximum earthquake for the any region. So based on the available data, when n reassembles the number of earthquake of magnitude m and a be positive real constant, which a denotes a seismic activity, say a log number of event m equal to 0, the estimation of a and parameter should be based on the complete data set. So you should know that the Gutenberg-Richter relation, okay, the recurrence model is applicable to the only a complete data set. That means you cannot consider the incomplete data set. So this limitation one has to remember when you do the hazard analysis. Okay, so you cannot take all the data simply fit a curve. It should be done only for the complete data. That is why we do a step method of completeness analysis to find out the data is complete for how many years. Okay, so that we follow now. So that data. So after doing the completeness analysis, so okay, you can take a data and try to plot, okay, log n, okay, versus m, and then you get a line. Okay, so that line, straight line you get. So that line, the A and B will indicate a what is the seismic recurrence of the region. So the number of earthquake n with magnitude m, A, B are positive and real constant. A describe the seismic activity, log number of event with m equal to 0, and B which is typically close to the 1 if the tectonic parameters describing the relatively abundance large to smaller shock. So if you have the mixed data, okay, so all the magnitude of mixed data, whatever happens in the region, then you can B will be close to the unity. Okay, you can see here. So the MC is a cutoff magnitude which has direct bearing on the estimation of A and B values, the Gutenberg-Richter relation. So the 9 method includes estimation of A and B and MC, which is suggested by Kitchko and Selwell. So where they are given a many statistical method similar to our MMAX estimation. So even there is a ready-made program called ZMAP. Okay, ZMAP. So that gives a calculation. So you can run using that code using the MATLAB, but how that works is, this is how it works basically. Okay, so statistically they also given a explanation. So this shows that the NM versus M, if you plot, you will follow this trend. Okay, so when you plot log n, this follow this trend. This trend basically the log m, if you take a lambda up m, okay, that is a annual rate of recurrence where Nm by T. So this follows a trend. This gives a return period of any particular earthquake magnitude. So you can see that log m and then the reciprocal is that period. So is the m. So if you want to know what is the m return period, so you can see this. Okay, so generally the smaller magnitude will have the shorter return period, a larger magnitude will have the longer return period. Okay, so this is what is estimated from the regional recurrence model. Okay, so you should make basically divide a magnitude as a different bin like 4.5 to 5.5. okay, so or 4.5 to 5 and take average value of 4.75 and then plot how many number of earthquake here and take a log m and then plot the next value. So finally after plotting that you can see that it follows a perfect straight line. So the equation which is like we have seen a minus b into m, okay, log m. So that a and b is your recurrence model coefficients and the equation is called as a recurrence relation. So the Gutenberg-Richter recurrence relation, so this is how it comes, like the 10 power of a and then the slope equal to b. So this can be also written like log m up, as I told you that it implies that earthquake magnitude exponentially distributed. So also can be written like alpha into b, that like alpha is equal to, so you can see right click, okay. So you can rewrite this by modifying like this, okay. So this is about the recurrence relation. So the recurrence relation, what really it means? The frequency of occurrence and magnitude. So if you assume that there is a 3, okay, curve 1, 2, 3, okay, let us see how the b value varies. You can see that the b value indicates a slope, okay. So the b value varies, but what about so the magnitude for the given magnitude of 6, what is the a value correspondingly, you can see. Okay. So here the b value indicates that high frequency seismically more active, which indicates that there is a large magnitude of earthquake. So the moderate seismicity and less seismicity where the mixed events are there. So this is about the b value description. So if we go to the b value only indicate the frequency of exceedance of higher magnitude. At lowest magnitude the frequency is same for all the 3 cases. So the b value indicate the frequency higher magnitude, higher b value indicates a less frequency or low seismicity. Okay. So this is what about the b value, how it varies. So the similarly you can take b value as a constant and then estimate a value. Okay. So you can see that a this 3, 4, 5. So the low frequency of small magnitude earthquake, okay, will have the low value. So the moderate frequency of small magnitude earthquake 3 and high frequency of small magnitude estimate a 4. Okay. So the a value only indicate a frequency of exceedance of lowest magnitude. So even though the b value is same, the lower a value will keep frequency exceedance, particularly magnitude as a low. Similarly higher a value will keep frequency exceedance high as a low b value. So this is about the how the b and a value for the constant 1 parameters. Okay. So this makes you to understand. So let us see what are the different b value we have got for the Indian region for the different researcher, my own work also. You can see that this is actually the Bangalore 2009. Okay. So we got the b value of minus 0.62 and a value of 2.14. So then again the 2009 there is a one more publication where we got b value close to the 0.9 and then 3.55. So then the Kalpakkam you can see the b value up like 1.13 and 4.98 is the a value. So Lucknow again you can see the values, okay. So this much. So then Haryana 5 and 1.25, Patna you can get 0.18 and 5.5. So then this is again the Gutenberg-Richter 150 kilometer radius. So is telling that the seismic steady area influences your Mmax. So not only Mmax, your recurrence relation also. Why? Because the number of data considered for the recurrence relations are different for different region. So okay. So the let us see the a actually shows the recurrence relation for the 150 kilometer where b value is 0.85, a value is 0.378, b represents a minus 1.08 and a value of 4.6 and c represents a 1.13 and 4.98. So you can see the a value b value difference. So the 85, okay, then 1.08 and 1.13. So this is about the b value. So the a value will be the 3.87. Okay. So then the 4.62 and then the 4.99. So this will alter your recurrence rate of the earthquake estimation. So this is the again a Patna for the, so the entire 500 kilometer radius for the typical plot. So these details you can find in some of our papers related to Patna and Kalpakkam, how this will influence the your hazard values. Okay, that is what we have done. So this is the typically the other studies for the different part of India. So Tarapur, okay, for the seismic steady area of 500 kilometer. So 4.85, 1.04. Vizag, you can see. Then the Haryana, you can see intraplate region. So northeast, boundary plate northeast. So the plate boundary Haryana. So the northeast, actually I told you that there is a complex seismotectonic. So we consider as a two part. One is that northeast intraplate region. So another is the northeast the plate boundary region. So you can see the difference in the A and B value. You can see. So that makes a lot of difference in your recurrence calculation in the PSH analysis particularly. So Tibetan Plat, the entire region, and then intraplate Haryana. Okay. So like that in plate boundary Haryana, intraplate Haryana, you can see the B and A values. Okay. So here you should see that the A, B values are is the function of how much steady area you consider and based on the your occurrence of earthquake in the region. Okay. So this will give you the indicate the how much the values are. So you tentatively obtained on the particular place, which is the function of the several earthquake reported in the any region. Okay. So the estimating of B value and A values are very important, particularly DSHA concern. If you want to go for the MMAX estimation by incremental method, then your B value you need to know. So otherwise in DSHA B values are less used, but in PSHA these AB values are used to get a annual exceedance. Okay, the model whatever you are getting now, that is the function of your recurrence model. So the PSHA analysis, probabilistic seismic hazard analysis. Okay, so where you get a very high importance for the B value. Okay, so the PSHA basically probabilistic seismic hazard analysis, you need to estimate a proper B value that influence your result of PSHA. Okay. So how it influence, basically we calculate a magnitude density function. So in the magnitude density function you can see that the beta. Okay, so the beta what we estimate basically from the your B value, you see the B value. So this is actually the what you get AB for the relation is actually the entire region. So that has to be reduced to the particular source. Okay, to know that how much the magnitude density function varies with the source. So that is like considering the length of the source and total length in the region, number of earthquake in the particular source, number of earthquake in the entire region. So that reduction is taken as a this one. So what you get the AB value for that is for the entire seismic steady area, that will be narrowed down to the particular source based on the this deaggregation procedure. So this comes in the PSHA. So when we there also we will discuss about that. So the scientist found that okay, the recurrence model whatever we said straight line, it is not always true for all the earthquakes. They found that the geological evidence shows that it is not a complete straight line. Okay. So it is not a complete straight line, there is a change in the pattern of B value when you consider a very long period data and earthquake. So the show a similar displacement of each earthquake, individual fault produces characteristics earthquake, that characteristics actually like geological data are to be modeled on this location, which does not follow this pattern. Okay. So there could be caused geological constraint, more research and field observation needed to take care of this, but right now they said that it is not a straight line to come and eat your MMAX. So you can see that one of the MMAX we use extrapolation of the recurrence model. So that they say that it is not always true. Okay. So that is what the characteristics recurrence of the earthquake model you can see. So with this basically we talk about the distance, okay, of the in seismic hazard analysis, how the distance are very important. We have also seen that okay, how to estimate a different way distance for different point sources, and then we have discussed about the recurrence model, which is a Gutenberg-Richter recurrence relation. So widely known as a GR relation, which is estimated from the complete catalog, okay, where you get a AB log. So n, okay, is the function of m. If you draw a line, that line will give you the AB value of the region. So that is called as a recurrence model or recurrence law, how the AB varies where the different region we have seen. Okay. The next part is, so once we establish the magnitude, the distance and recurrence relation, the next is basically the predictive equation which you are going to use for the hazard analysis. So that part we will be discussing in the next class. So thank you very much for watching this video. So I will meet you in the next class. Thank you.